Thank you very much. Well, thank you for inviting me and thank you all for coming. And actually, I will do some publicity, public relations for my degree, so you might be interested in. Apologize for the bad design. We're obviously a technical school. We don't have any ideas of aesthetics. We're a University of Applied Sciences, so we educate for a slightly less academic and a slightly more applied level. Well, that's the settings where we're situated in, and we have also a degree of biomimetics, a bachelor's degree actually for biomimetics, which has a big advantage because you get fresh, open brains, and we have 3 years to form then to think highly interdisciplinary, and that will be a first introduction into my talk. The rest of the talk, to give you a short outline, will be a series of examples we work on or have worked on in the past. Being a biologist, I somehow had to incorporate a somewhat biological scheme, so it will all be grouped around arthropods, meaning insects, spiders, and a lot. So I left out the frogs and other animals, and I had to leave out unfortunately, some industrial projects for the very sake of any kind of picture that was generated there. Was not allowed to be presented, so obviously Eric signed a better contract than I did, or we did. So smart infrastructures. If you want to do biomimetics and you want to teach biomimetics, you kind of need a surrounding that allows to do that, and that is, I think, one of the unique points in our area, in Germany, that we have a group of people with completely different backgrounds actually sitting in the very same corridor and working together. So we have a physicist, we have an engineer, we have me, zoologist, and long biomimetics involved person. We have a botanist, which is completely different from zoology. We know all that. We hate them, we fight them, no, not that much. And we have a polymer science person. And next to that, we're situated in the Department of Mechanical Engineering. So we have all the row of engineers that you need to get the stuff actually working. So I'm focusing, we set up our degree in 2010. We started educating that. So now, after 5 years, we're in the re-accreditation and to improve it. And in the same time, we established an institute, research institute, that actually tries to come up with smart ideas for integrated products that combine the structural part and the integrated sensing part, which is obviously quite a challenging task, as you know, but it stems from our 2 focus points of structural engineering, which is the mecha in mechatronics, and the information part, which is more the tronics and which is mirrored by the biomimetics field there as well. So we have a lot of nice fancy tools, which I don't want to talk about in detail. Where is the pointer? Didn't have a pointer. Ah, there's one. So what you see up here is one of the nicest tools. It's a 3D high-speed camera, so it's 3 high-speed cameras, 6 to around about 6 lights to film actually insects during flight, which you will later see some videos from one perspective. The funny thing here is to get those 9 axes perfectly aligned, and then to do the analysis of a small, tiny insect motion. And a lot of nice other instruments to do biomimetics, from the whole analyzing the biological system. So to go into a biology lab, to do microscopy on the specimens, to go into the materials lab, to analyze the material properties, to analyze locomotion, and then to reproduce it by 3D printing, by building the controls and the microcontroller architecture, and doing enough simulations in between to make sure it actually works. So we have the tools at hand to really go from bio to bionics, we say in German bionic, to the technology part, and to basically work our way through. And this allows us, of course, to have a significant depth of innovation in that sense. So I don't know if that is disruptive following your definition, but surely we have the possibility to be disruptive enough. And if you look at biomimetic, at the famous examples, for example, like Velcro, studying the interaction between the seeds, the burn, and the dog by this Swiss engineer led to a product that didn't exist before and solved problems no one had before. But nevertheless, it is a very, very successful product that didn't at all look like the optimization of a shoelace. And this is kind of the idea which we try to transport to our students. And that's why we give our students a lot of open tasks. So we don't say this is a machine, make it 10% better, but we give them a very vaguely defined job, and then they shall come up with ideas and product ideas and put them into practice. And one of them is a very nice smart structure made by our students, which is this lightweight piece of tooling. What's that in English, actually? I don't know. It's a fork wrench kind of thing. So you use that in every day if you repair your bicycle, your car, or your ship, whatever you have at home. And what they did, first of all, is they cut it off here and replaced the lever you see it here at the end, not by steel, by some carbon fiber, glass fiber mix, which makes it much lighter. Nice. Does it work? Yes, it works. They looked at tendon-bone interaction to actually get all those fibers aligned and somehow interacting with the steel here or with the original steel here on that part to actually transmit the force into the tool's head. And actually they passed the standards defined in the ISO standardization for that tool. What they also integrated here, and that's the insect part of it, is this slightly little cavity, which actually represents a force sensor of insects, very, very abstracted, but that was the initial idea. And that allows them to measure the moment when you pull the screw, when you tighten the screw. So you have the same tool, but with much more added functionality and lightweight. And that is kind of part of our education, where we want to get the students to think outside and to come up with new products that might look like the old one but have a significant change in functionality. So does the customer want that? That was a big discussion in the beginning. And honestly, I have no idea. This is a part where I have no real expertise in, so that's probably the part we are weakest in. But we collaborate a lot with companies, so we try to get our feedback there. So to get to the series of different models I want to show you, first of all, arthropods. That's insects and spiders together, roughly said, for all non-biologists. So this kind of general Bauplan where you have this exoskeleton, you have this kind of a tube, in the middle is all the muscles and liquids, and outside you have the outer shell which transmits the forces. So it's kind of a knight in shining armor, but the armor is actually the real structure. And scorpions are part of the arthropods, and scorpions have a very nice feature. And when a scorpion stands on sand, that's not our results, and you tap the sand somewhere, and that's quite nasty, scorpion is capable of detecting where the tapping comes from. And this is quite good because scorpion is nocturnal, so hunts in the night, and as we know, vision is a challenging task at night. And when an insect passes by or something, well, maybe a small mouse, just by the transmission of the substrate vibrations, the scorpion is capable of detecting these vibrations and knowing the direction and also the distance to a certain degree where to go to hunt for the prey. We didn't do all the research. We took what was available in literature, and actually it was our students who started off with that. And they, first of all, programmed, because that's so much easier, a neural network that would allow the detection inspired by the scorpions. These are the 8 legs, and you see this is the surface, the substrate wave that comes up to the one leg, and the neurons then inhibit on the other side lying legs, and you have a series of inhibitions that kind of allows the scorpion to detect where the wave is coming from, and then a second layer of neurons that allows to make this assumption to a degree of about 3 degrees offset. So to a precision of about 3 degrees, they know where the vibration is coming from. And immediately they came up with a mock-up of this sensor, which unfortunately is technically not that simple. Neural networks are good for very high parallel processing. This is a simple Arduino, so you don't have much parallel processing. And this is actually where the research project started, because we thought this is a very nice product, but actually how can we put this into a working product? And you see the first thing, we put it to an engineer, and they reduced it to 6 legs, thinking it was an insect. But we have come up with a couple of nice ideas, which is currently in the doing. But this is the inspiration that it can take on from a student project into a research project, and that is working quite well. What do you use this sensor for? The sensors are, for example, interesting in knowing where people are moving. So if you have a person at home that is kind of sick, you don't want to video survey them the whole time, but you want to know if their motion is still intact and where the motion is. Or you could turn any kind of board into an interface. So that's about the application of that, derived from a biological research result, like the vision for Toyota. This is a product that we are technical design, which we're working on at the moment. But it is really, the big challenge is here to be fast enough to detect substrate waves. The problem is that sound moves much faster in the substrate than in air, so we have more of an engineering problem than a biological one. But arthropods are a great source of inspiration, and if we stay at the arthropod leg and move from scorpions to spiders, we can find a completely different system, same basic plan, where it is derived from, a bit of a different area, and a completely different function. If we look at spiders, you know spiders usually build their nets. That's what the common idea is of a spider. Builds a net, it waits there for the prey, and then catches the prey. But actually, if we watch out, there are a lot of spiders that actually do not live in nets, also in our areas, that just walk around and hunt freely. And some of those are, for example, called jumping spiders for their very habit of really jumping at their prey and catching it with their feet. So what they have to do is not handle a thread, but they have to handle smooth surfaces. And that was a research where we had a look at the feet of spiders, and this is actually the end of the foot, the tarsus of a spider. So you see here basically that tube with a lot of hairs around. You see here some hooks, and actually in the net-living spiders, those hooks are much larger. They are used to handle the threads. And here you see this soft, flurry thing. It looks a bit like, yeah, it's a bad picture, bad resolution. But if you look in a bit closer, and if you magnify a bit, we see that these little flaps are actually covered with hairs on the back and on the front, so they have a bilateral symmetry. And here the hairs have pointy tips, and we don't know yet what it exactly is. If we go in a bit more, we see that they have these triangular shapes. Now, what are these shapes used for? And we had a look. There's a weird little invention called the atomic force microscope. It's a microscope to look at small structures, but it's force-based. So the idea is that you have a small mechanical tip, a real tip of silicon, that interacts with your sample. And then you have a mechanical force that results in a deflection, and this deflection you can register by pointing a laser on the back of the cantilever here. And this is used, well, this microscope would have gotten a Nobel Prize for the inventor hadn't he gotten one a couple of years earlier for another microscope. So that train was passed. So you can use this to image three-dimensional structures in the microscopic level, and to actually not only get a visual impression, but really get a three-dimensional landscape. And you can also use it for so-called point spectroscopy. So you put it down on the object, you pull it up again, and that's exactly what we have here. You push it down, it snaps in, you press a bit, you release, and then you pull it away, and it sticks a tiny bit. And that sticking a tiny bit here actually gives you the adhesive properties of your sample. Now, if you want to measure adhesive properties of something like that, well, you can attach it to something, but you don't really know how much of your hairs really get in contact. You can roughly estimate how much hairs there are, but you don't know how much you get in contact. It's a bit like with a Velcro. You can push it together and you know it'll hold, but you don't know how many hooks are actually interacting with the velour on the other side. So we wanted to measure them individually, and that's what we did. And we could measure forces here of something like 20 nanonewton. That's not a lot. It's quite little. But if you look at the leg, we did some counting, a lot of counting, and then some estimating. And the whole spider manages to get about, let's say, 500,000. Let's give a rough estimate, 500,000 of those hairs. Now, if you have a couple of 20 nanonewtons or 30 in other values, and you time it with 500,000, you get to the fact that the spider, using 6 legs, could maximally hold 100 times its own weight if all the hairs were in contact. Yeah, that does, of course, never happen. It happens with a Velcro. If you press like for half an hour and you make sure that every little hook gets its counterpart, then you have a maximum hold. But it maybe illustrates quite well that if you put all 8 legs, you round up with about 160 as a safety factor. You can imagine that this spider is quite easily capable of holding on to things, and maybe even holding on to prey and catching the prey with some legs and holding on to the substrate with other legs, and going food shopping in that way, without reaching the maximum capability of its hairs. Now there are a couple of problems coming up here. The one is the dynamics. So if you jump around and you catch your prey, you have to get the hairs into contact with anything. And together with some Italian researchers from Udine and now in Bolzano, Bozen, we did first some mechanical analysis. And actually what comes out is this foot is, one more picture back. Here we have the foot, we have the seta and the setiole. So we have 3 different structural elements which are spring damping mechanisms. So we have a 3-step hierarchical spring damper. What does that say? That helps us to bring as many hairs as possible in any kind of substrate, to contact with any kind of substrate, and not 3 hairs are sticking and the rest is hanging in the air. So that's the important part, to, if you have little single force, to get enough of those little hairs into contact. So 3-level hierarchy in spring damping allows for adaptation to any kind of substrate geometry. First. Second, sticking is a fine thing. Sticking things together is great. The problem is then getting it off again. So the spider doesn't want to stick to a substrate and then be there for the rest of its life, or it doesn't want to stick to a prey and like catch it once and then eat that one till it dies. So it has to get rid of it. It has to move. It has to tighten the adhesion. And there is some very smart mechanism that we see here when we look closely. These terminal ends of the setioles are actually triangles, and they're slightly bent. So there's not a tip, but it's a bit like that. And they are pointing outwards. So when when the spider hits with the foot on the ground, there's great adhesion achieved. However, if the hair gets tilted a bit in that direction, if the angle of attack changes a bit, so just by pushing the foot out or by rolling it a bit, the contact will go away from a triangle and move towards the tip, to the flat side, and drastically reduce. So detachment comes for free. So it's not like you put a lot of glue on your feet and you can attach, and then you stick and have to have the same force to remove again. No, you can detach for free. So that's a very interesting adhesive system that works without the use of fluids. It works with van der Waals forces. And yeah, it's great for technical application. Now guess what? It's not that easy to produce. So we have a group that in Germany that works a lot on those kind of attachment devices. And after many years, they're now capable of producing those devices that peel off, but surely do not show these asymmetries. So that's part of production. How can you produce this kind of devices that actually allow for that kind of sticking and removal? But in theory, it would be a very good thing to have if we could reproduce it. So spiders, don't just kill them. Take a second before you kill them and think of the great technical innovation they have. And not only the jumping spiders, but also the spiders that produce silk. And we know the story. Spider silk, super strong, stronger than steel, would be the perfect material. But it is only elastic and it is transparent. And it's probably one of the only optic material that is actually transmittable, that can be perfused by chemical compounds that are solved in the air. But glass surely isn't, and PVC also not. So what we tried, we worked together with some spider silk people and said, okay, we have a lot of those technical stuff in our lab. How is it? Can we actually couple a laser into a spider silk? Now, technically, this is possible, and thank God I know a laser physicist, because if you look at that, my slides are probably not perfectly aligned. We have 3 microns diameter. So if you want to hit with a light point into 3 microns of diameter, you have to not only hit it, but you have to be aligned. It's quite challenging, let me tell you that. Yes, our cold atoms physicist managed to do that. Then we have the spider silk, of course, we have, which is basically a lot of proteins, let's say. And proteins are arranged in that manner. So we have here the spider silk in the microscope. You see a bit the dark edges and the transparent center. And there, if you look into it, that's a micron thick. This one, 3 micron, that's already the biggest we can get, actually. They're usually thinner. And you have these protein threads and these sheets of proteins where it's folded into packets. Now, what you can do with a packet, if you pull that, so that's the spider silk if there is no strain, and if you start pulling, these packets dissolve and change their conformation. So piece by piece, you get a different product. It just doesn't stretch like a piece of PVC. It changes a lot in its polymeric configuration. So if you pull light through it, you might be able to see that change in the intensity the light comes through, in the modes of the light that comes through, and maybe in a shift of wavelengths. So you can put a strain onto something, you can put a light through and see the changes, so you have a perfect sensor. And now what else I said is you can put, it's transmissible for chemicals. So if you put receptors in protein engineering, that's possible, for any kind of toxins, you can add them to the spider silk, and if a toxin docks, you would have a change of conformation, leading to a change of strain, leading to a change of light output. So you can produce, in theory, a sensor that is not only acting on single molecules, but also on, you could dotate it to be acting for 20 different toxins. Why would you want that? If you have a toxin sensor and it goes off, you don't really are interested in which kind of toxin is killing you. You just want to get the hell out. So you can make a toxin sensor that is going off for 20 different toxins or I don't know what, that will be able to detect toxin at a very low level and be able to give you an alarm to leave the premises, and then afterwards you find out what was about to kill you. So we have a setup to test that. We have a setup to pull the light, to pull the spider silk, but yes, frankly, it is a very challenging task to pull spider silk and still keep the light on shining through, because we have a margin of error of about a micron, and when you pull stuff, keeping a margin of error of a micron is not very easy. But yeah, that's an ongoing experiment, technically very challenging at the moment. In principle, could be giving us a great deal of a completely new product as a multi-functional toxin sensor, for example. Working on it still. But my career is young, so I have still time to do that. And actually, I have to say, it's not entirely biomimetic, it's more bioengineering, but the customer will not really care in that moment. So, spiders. We've had enough of those spiders, creepy animals, probably the least liked insects. First to those ones, earwigs. Those you know from, for example, you use them to protect your cherry trees. At least we do that in Germany. We try to have them close to cherry trees, and then they eat the lice. What you probably don't know is that these animals are actually quite beautiful. Not in this state. In this state they look weird and ugly, but in that state, when they actually want to fly, when they unfold their wings, they have beautiful wings. The only thing is, they don't really fly. They've hidden their wings here behind those little elytra, and this is actually the elytra that's already a part of the wing, so they have to fold it very, very small. And when they fly, they have to unfold it, and then can use it to fly. And that they actually do fly, I can show you in that next video. So the wings are unfolded, and you see, it's taking a bit of a break. The earwig will someday decide to finally make it and fly and lift up in the air. Of course, insects fly a lot, but these wings are folded to a 20th of their original size when they're packed together, and can be unfolded and are strong enough to hold the insect in the air while beating its wings. So that's kind of interesting. It's lightweight design, of course. It's high performance, it has to be stiff, and it's, of course, very great folding techniques that have a bistable function. So we wanted to work on that. And the first idea is, okay, where do we get those? And I sent off my PhD student. I'm very thankful for that decision, because this is where you get them. Horse dung. And that also gave some publicity to my PhD student. Apparently, German press loves it when PhD students stand knee-deep in horse shit. So she ended up in TV a lot with showing the camera how to get massive amounts of earwigs. So you have to know the right places in the horse dung, and then you can exhaust them with a little mouth-driven hoover. And you can collect them and then try to rear them in the lab. And do a lot of work on that. So this is roughly how the wing looks like. If you draw it, you see it a bit more in detail. We see that here, this is where the insect is on the left side. This is the part you see when it's folded. That is actually the corner you see when it's folded. And all that stuff gets neatly packed in and folded together. And I will show you what that means later. So these small dashed things, those are lines where it gets folded, and the black longer ones are reinforcement parts in the structure for good mechanical design. And actually we see like 3 different kinds of folding. So the most simple one is here, this fan-like structure, which you might have already guessed. So it folds like a Chinese fan. Then we have here 2 transversal folds that fold the fan in itself, and then it all gets packed through the longitudinal fold underneath the more rigid upper squama here. That's the only insect in terms of folding that has all three folding techniques known in insects combined in one wing. So that's kind of a technical challenge. What we don't see here are the radial veins that I showed you before. The long black ones are the radial veins. They go through the whole wing, and these intercalary veins that are between the radial veins. And yeah, the ones bend to the one side and the others bend to the other side when folding. Now, this is not just a stiffening element. We had a look at it, what else of what kind of material properties in it. And actually, what we found is that they were blue under the microscope. Well, there was a trick. There was an ultraviolet microscope, and there's a protein called resilin. That's like the ideal rubber protein. That's the perfect spring for insects, biomechanicists. And if you put ultraviolet light on it, it automatically reflects blue light, so you don't have to do any staining. You just hold it under your microscope and you see everything that reflects here in blue is basically a spring-like structure that is able to store mechanical energy. And we will learn later what that means. Then next thing we had a look at was the motion analysis, and you see here the setup with lots of lights, and here this is a camera, and there's a camera, and there's one in the back, and here is the place where the insects were. So we tried to have them run up a little structure where everything would be in focus. Now guess what the animals don't do? Well, as previously said, when they don't really like to fly. When they are in danger and want to escape, what they do is usually just throw themselves off. They know their body is rigid enough and will easily sustain an impact, so they just throw themselves off when they're in a hurry. They fly when they want to relocate to a different place of horse dung, for example. And turns out that actually it's best when you catch them on a slightly almost rainy day and put them into the dry lab. Then they like to fly most. This is when engineers, usually you look at us with really weird eyes, but that's the magic of the biological research. And here we were able to record them at 1,000 frames per second from the 3 different perspectives. And with quite some patience, you manage to get videos like that. I have to click. Now you see why they don't fly when they want to escape. So it takes some time and preparation. And then they fly off. But what you see here a bit, stop. You see here, for example, those are the elytra, so the covers of the wings that kind of just stand out during flight and don't disturb the animal a lot. So looking at the wing, we have a lot of different features that we found. So we saw these ones here in the wings, the elastic elements. And actually what they do is when the wing is deployed, in its deployed state, they produce lateral forces along the surface. And they kind of interlock the whole surface in itself and produce forces that prevent the folding a bit. We see that those weird bendy shapes here show different colorings. And actually, this is where the folding line goes through in that part, where they act as, they sometimes have to go around. And on the other side here, they have to go inside the fold and stabilize the fold. What else do we see here? If we look at the top, these are 2 different species, but here you see it better. On the left side of the wing, so the insect is here on the right, they're a bit browner than here in the inner side. And that means the cuticle, so the structural element, is stiffer. So the wing is mechanically stiffer on the outer side and softer on the inner side. And then if we look here, what we see later on, also the veins are differently attached to each other. So there's a lot to take in. The first thing is there's a lot of prevention mechanisms for the soft membrane to not tear. You have a very thin membrane, so that shouldn't tear, otherwise the wing goes pear-shaped and is broken. Then we see those hinges that some of the long radial elements are joined and others are freely, and actually that allows the wing to be stiffer on one side and more compliant on the other element. And that leads to that part when it is actually flying. And here I highlighted for you the leading edge, so the front side of the wing when it is actually beating. That's a series of high-speed images. And what we see mostly is that, even from the different perspectives, that the leading edge is changing a lot its shape. Now you could say, okay, that's we need for flying, but it also has a second effect. When the leading edge is not straight but slightly bent, it prevents the whole wing in the back from folding together. So actually the mechanical load puts the wing in a locked-in mechanism, rotating around this axis roughly, so the insect is here on the left, and this whole part flips back and forth and prevents all those folding lines from folding back together. So the wing is in flight a self-locked, unfolded, in a self-locked state, and is capable of keeping the load. And yeah, it can be folded in later on. We did some simulations, or trying to. That's just the kinematic simulation done in the CAD program, trying to get that animated. And you have a lot of tear and elastic elements in there, so designing that in CAD is not that simple. And thank God I didn't have to do it with my zoology degree. But one of our students did. And yes, that simulation will then go on as a next step into force simulations to see actually which forces act on the different parts of the wing while being folded, unfolded, or during flight. Looking at those wings, we have already seen a lot of different functions. We found a couple of more integrated. So we see, for example, in the electron microscope, these long protruding elements and these small little ones. The small bumps could be have a function we don't know yet, still something like a particle repellent, like the lotus effect, to clean the wing by itself. These rods could be, maybe have the function as distance keeper during folding so that the wings don't actually stick together in a folded state, but keep some level of air between. And here we're quite sure that we have found some sensors because these are hairs with possible sensory cells below. So this is a very combined product of nature with a lot of different functions in one, with a lot of very astonishing performance parameters and ultra lightweight. Now, putting that into a product is the next challenge, of course. That'll be the next PhD probably to work on. And yes, just to give you a last example how great evolution is and how perfect it is. Once more, evolution never fails. Animals never make mistakes, or sometimes they do. So this little friend was basically way too eager to fly off and didn't secure actually the unfolding of the wing, and then they drop off. So not everything's perfect in nature, but at least it's fun to watch it. I thank you a lot for your interest, and I hope to have conveyed a little bit of my fascination for those little creatures, and hope you come up with great product ideas. Thank you.
So the small bumps on the surface of the wings of the earwig, could they also be to increase transparency of the wings?
Now that you say it, yeah, maybe.
Yeah. And have you done contact angle measurements on the wing to see if it's actually hydrophobic?
We haven't done it yet.
Okay.
We actually have the instrumentation, but we haven't done it yet.
Okay.
What we use, it should be quite repellent, because one trick we use is to put the whole wing on water to unfold it. And that's quite a challenging task, but it's the easiest way to unfold the wing when the insect is detached from the wing.
Right.
Or the wing is detached from the insect.
Thanks.
Have you been using the folding system somewhere in the industry?
No, by far not. We are at the moment really at the point where we slowly understand how it works. So the next step is to create a mock-up. And then we can go to industry. So that's nice pictures, but industry, that's exactly that, nice pictures, entertainment. We have other stuff where we didn't look that far into biology, but started at a further state of research. There we go closer to industrial applications, for sure.
Do you have some places where you would like to use it? Or?
We have close by a couple of companies that deal with lightweight carbon fiber and glass fiber structures. So there we would be very happy to introduce it as a mock-up and see if we can basically have structures that we can unfold and then make them rigid to use and just fold together, or for a once in a lifetime unfolding, which would facilitate transportation and a lot. So that's as a general design principle. That's the idea.
I guess space applications one could think of. I mean, a lot of things have to be very compact when you transfer it up into space.
Yes, space is one point. The problem about space is the market's very small. So that's one problem. So you have usually 1 or 2 launches that has to work like 1,000%. So the risk-taking is not very high in space operations in general. And also the killing of ideas, I don't know where the idea killer is sitting, is also very big. So you start off with 100 really great ideas, and 20 years later one of them gets launched. So we rather aim for a bit of an industry that has a bit higher output numbers.
Right. I think it was a very good question about industry, because I guess you're in the same situation as many of the rest of us, that we have insight into smart technology in nature and other places and are seeking applications. I guess NASA was in that situation after sending all the men to the moon. They have invented a lot of technologies, not necessarily from nature. And they used a lot of effort in trying to promote these technologies to different companies. I don't know, have you any idea, or I don't know, how does this work in Germany? I don't know if it's something special in Germany, but
well, I can speak with some experience from ESA. Mm-hmm. They have a lot of initiatives, the technology development triangle, so the one part of developing the technology together with industry that's not space related, and the other part marketing self-developed technology to industry. That is programs, like, you know, European-sized programs with their speed and bureaucracy that we all appreciate. But nevertheless, there's ongoing activities. What we try here on a smaller scale is we have a project that's funded by the inter-regions, like European regions of different countries, adjacent countries. So we're together with the Dutch across the border. We're in a project that we deliberately work with SMEs, trying to get those technologies into SMEs. And the problem with SMEs is that they don't really have their own big development parts, development departments. And that, for example, is way too advanced for SMEs, but yeah, simpler solutions are working, and we can bring them into. That's, for example, we work with artificial mussels or with the sandfish skin to put the sandfish skin, for example, is in a big evaluation for a company that produces recycling machines and need to keep the inner sides of the machines clean. So that's working, but you need a specific funding program or a specific established program that promotes it and makes it, at least at the beginning, for free for the companies. That's my experience. So if it's for free, they look into that. The problem is we need to pay the people, so then funding comes into place.
Right. Any more questions? Doesn't seem to be the case. Well,
thank you.
Thank you to you for